The first section in this chapter is about discrete random variables. A random variable is a numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as x. So these are variables just like you would have talked about in algebra, x, y, z, and so on. The variable has a single value for each outcome of a probability experiment. And a discrete random variable has either a finite or a countable number of values. Earlier in this class we talked about discrete data versus continuous data. We also have the same distinction with random variables. We can have discrete random variables and continuous random variables. So remember that discrete data talks about something being countable. Countable refers to the fact that there might be an infinite number of values, but they result from a counting process. The values can be plotted as points on a number line with spaces between the points. So remember, there are gaps between the values. Here's some examples of probability experiments and the discrete random variables that would go with them. So one probability experiment would be rolling a die. The sample space, in other words, the set of outcomes for what comes up on the die, are the numbers 1 through 6. So for this one, our discrete random variable x would have possible values of the whole numbers 1 through 6. Another experiment would be selecting a part and inspecting it. Now the possible outcomes for this experiment would be either that the part's defective or that it's not defective. Now when we're defining a discrete random variable, we have to give it numerical values. So we would have to define some numerical values to represent defective and not defective. One way this is done a lot of times is using 1 for one of the values and 0 for the other value. So one way we could define a discrete random variable for this probability experiment would be to define defective as the value 1 and not defective as the value 0. Another experiment we could do would be to play a game where one playing card is drawn from a deck and the player wins or loses money depending on the suit of the card drawn. So the possible outcomes when you draw a card from the deck and only look at the suit are the 4 suits: hearts, diamonds, clubs, and spades. Now again, to define a discrete random variable, we have to give those outcomes numerical values. So if we're playing a game and we're winning or losing money depending on the suit, then we could assign each suit with the amount of money that we would win or lose if we drew a card in that suit. So here's some possible values for x. For example, if we won $2 if we drew a heart or a diamond, then those would be the numerical values for those two outcomes. If we won $3 by drawing a club, that would be the numerical outcome for that outcome. And if we lost $8 if we drew a spade, then we would make our x value -8 to signify that we lost money. One more experiment is drawing 5 M&Ms from a bag with replacement and recording the number of red M&Ms drawn. So our possible values for our outcomes are just the total number of red M&Ms that we drew out of the 5. So we could have gotten anywhere from 0 red M&Ms all the way up to 5. So that is our sample space, and we can define our discrete random variable as having any one of those values. Now let's look at some examples of discrete probability distributions. If you remember in Chapter 5 when we talked about probabilities, we did talk about probability distributions. And all we did was create a table that had the list of outcomes in one column and the probability for each outcome in the second column. Again, a discrete random variable has to have a numerical value. So when we're creating a discrete probability distribution, we have to list the variable such as x and its numerical values. So for the experiment of rolling a die, this is what our probability distribution would look like. So we have x, which is our random variable, in one column, and the other column is the probability for each value of x. So our possible outcomes for rolling a die, our numerical outcomes, are the values 1 through 6, and here's the probability for each different outcome. Since each of those values is equally likely to come up on the die, the probability for each one is 1/6. So this would be our discrete probability distribution for that experiment. Now for the experiment of selecting a part and inspecting it, we have to know a little bit more in order to create our probability distribution. So for this experiment, let's suppose that 8% of the parts produced are actually defective. So here's what our probability distribution would look like. Now we can list the outcomes in words over here, but they're not technically part of our probability distribution. Our probability distribution is really these two columns where we have the variable and its numerical values, and then the probabilities for each value of the variable. So in this case, if 8% of our parts are actually defective, then the probability of the part we select being defective is 8%, or 0.08. And we decided to give defective the value 1, so here's the value of our variable, and here's the probability for that value. If the part's not defective, we gave that a value of 0, and the probability of it not being defective would be 92%, or 0.92. Now there are two conditions for something to be a valid probability distribution. First, the probabilities all have to be valid probability values, so they all have to be between 0 and 1. We can't have any negative probabilities, and we can't have any probabilities that are greater than 1 or 100%. The other condition is that the sum of the probabilities in our distribution has to be 1. So if we add up all the probabilities in our table, they have to add up to 1 or to 100% if we're listing them as percentages. Now let's look at an example of discrete probabilities in general. And this is the same experiment that we talked about earlier, where we play a game where one card is drawn from a 52 card deck. If the card is a heart or a diamond, you win $2. For a club, you win $3. For a spade, you lose $8. So what's the probability that you win money on one play? What's the probability that you win more than $2 on one play? And what's the probability that you lose money? First, we're going to construct the probability distribution table for this game. And remember the two conditions that we just talked about. The probabilities have to be between 0 and 1, and the sum of the probabilities has to be 1. So here are our outcomes in words. We can list hearts and diamonds in the same row because they have the same numerical outcome. For either one of those, you win $2. Clubs has a different outcome, that's that you win $3, and spades has another different outcome in that you lose $8. So for our numerical outcomes, we're going to use the amount of money won or lost, and if it's a case where you're losing money, we're going to make that a negative number. So our numerical outcomes would be 2, 3, and -8. The probabilities, since there are the 4 different suits and an equal number of cards in each suit, then the probability for each different suit is 1/4. So here, since we have 2 suits combined, the probability there would be 1/4 plus 1/4. For the other 2 suits, each one of them has a probability of 1/4. So here's our final probability distribution. We have our numerical outcomes here, And here we have our probabilities. It's 1/2 for a heart or a diamond, 1/4 for a club, and 1/4 for a spade. And just to check that we've computed these probabilities correctly, we can add them up, and they do add up to 1. So now that we have our probability distribution table, we can easily answer these questions. So what's the probability that you win money on one play? Well, you'll win money if you draw either a heart, a diamond, or a club. So these are these two numerical outcomes, either a +2 or a +3. And to get the total probability, we can just add those two values together. So the probability of this would be 1/2 plus 1/4, which is equal to 3/4 or 0.75. What's the probability that you win more than $2 on one play? Well, you will win more than $2 only if you draw a club. That's only this outcome, so the probability is just going to be 1/4 or 0.25. And finally, what's the probability that you lose money? You'll lose money if you draw a spade, so the probability again is 1/4 or 0.25. Now notice that this is also the complement of winning money. You're either going to win money or you're going to lose money in this game. So losing money is the complement of winning money. We already found the probability of winning money was 3/4 or 0.75. So we could find this probability by subtracting that value from 1, and we'd get the same answer as we got by finding the probability directly. And a probability histogram is just like a relative frequency histogram. The only difference is that the vertical scale shows probabilities instead of relative frequencies, but they're basically the same thing. So for a discrete probability distribution, we usually use 1 bar for each value of x, or 1 bar for each outcome. Here's an example of a probability distribution. In this one, you can see that the values of x that actually have positive probabilities are anything from 4 up to 12, and all the whole numbers in between. So for example, you can tell that the value with the highest probability is 10, the value with the lowest probability is 4. So let's look at probability histograms for some of the experiments we've already talked about. Selecting a part and inspecting it if 8% of the parts are defective. Here was our probability distribution, and this would be our probability histogram. We have our two outcomes, 0 and 1. Each one gets 1 bar, and the probability for the 0 was 0.92. The probability for the 1 was 0.08. For rolling a die, we had these 6 possible outcomes, and each one had a probability of 1/6. So in this one, every outcome has the same probability value, so this goes straight across on the top. Each one of these outcomes has a probability of 1/6. Now for our game with the cards, we had 3 different outcomes. So if we show these on the graph, we have the -8 clear over here, and the 2 and the 3 over here. And our probabilities were 1/4 for the -8 and the 3, and 1/2 for the 2. So these are our values. So the mean of a discrete random variable is given by this formula, where x is the value of the random variable, and p of x is the probability of observing the value x. So what this formula tells you to do is for each value of x to multiply the value times its probability and then add up those results, and that gives you the mean. And again here, the mean actually represents the center of the data. If we think about our probability distribution as being sort of like a frequency distribution, we can look at our probability histogram and make an estimate as to where the center of this data would be, or where the mean would be. In this case, our highest value was for 10, And so we could make an estimate that the mean of this distribution would be somewhere around 10. Now to actually compute the mean, we use basically the same process as we did for computing the mean of a frequency distribution. Only instead of class midpoints, we just use the values of the variable x, since we've got discrete values. And instead of frequencies, we're going to use the probabilities in either decimal or fraction form, not in percentage form. Okay, so let's look at how we would find the mean of this probability distribution, which represents the number of DVDs a person rents from a video store during a single visit. So our possible values of x are everything from 0 up to 5, meaning that typical customers who come in might rent anywhere from 0 DVDs up to 5. Probably in this case, the store has a limit of 5 DVDs in a single rental. And here are the probabilities for each one. Now, if we look at our probability histogram, we can see that the value with the highest probability is 1, and this distribution is skewed to the right, which means we have a longer tail on the right, but the center of our data is somewhere around 1. It might be just a little bit more than 1 because we have more values on the upper side of 1 than we do on the lower side of 1. So we might make a guess that our mean is a little bit larger than 1. Now to actually compute the mean, we're going to take our table, we're going to add a column to it where we're multiplying each x value times its probability. So we're just multiplying across in this table. So here we have 0 times 0.06, here we have 1 times 0.58. We're going to do that all the way down, and then we just add up the results that we get, and that's our mean. Now you can also do this with your calculator. In order to do that, you would enter each x value into your L1 list and enter your probabilities into your L2 list. Then use the one variable stat function, and the mean will be the x bar, just like it was for everything else when we did one variable stats. So either way, if you calculate this mean, you come up with 1.49. And that matches with what we saw in our probability histogram. Back here, we estimated that our mean was a little bit bigger than 1 because of the shape of this distribution. Now the big question with the mean for a probability distribution is, how do we interpret it? So the mean of a random variable represents the mean of the outcomes of the experiment in the long run. If the experiment is repeated as the number of trials increases, the mean of the actual outcomes gets closer to the mean of the random variable. So the mean of the random variable is also called the expected value because it is what we would expect to happen in the long run, and it's sometimes denoted by a capital E of x. Here's an example for expected value. The probability distribution that we already looked at for the number of DVDs a person rents from a video store during a single visit had a mean of 1.49. So let's interpret this as the expected value of our random variable x. Our expected value is the same as the mean, which was 1.49. So to interpret this, we'd say consider each customer's visit as one trial of this experiment. In the long run, the average number of DVDs rented by customers during a single visit is 1.49. Now, we're not going to have any one customer come in and rent 1.49 videos, obviously. But what this tells us is that for most customers who come in, they're either going to rent 1 or 2 videos, so that the average is going to come out to be about 1.5. Now, if you're the store owner and you're wondering how many videos you're going to be renting out during a certain number of customer visits, you can use this expected value to help you with that. For example, in 1,000 customer visits, the total number of DVD rentals we would expect is 1,000 times 1.49, or 1,490. In other words, again, the average number of DVDs rented by a customer during a single visit is 1.49. So if we take that average times the total number of customer visits, we get an estimate of the total number of DVD rentals we would expect in those 1,000 visits. Let's look at another example for expected value. This is from our same card game, and we have our probability distribution already, so we can find our expected value, and this is an easy one to find by hand because we just have a few values of x. So we're going to add a column to the table for x times p of x, and then we're just going to multiply across. So here we have 2 times 1/2, here we have 3 times 1/4, and here we have -8 times 1/4. And it is very important while you're doing this to include the negative numbers, include the negative if you have a negative value of x like we do in this case. So what we would get from multiplying these 3 values is here we would get a 1, here we would get 0.75, and here we would get -2. Now if we add those 3 values together, we end up with a -0.25. So that's the sum of this column, and that is our mean or our expected value. To interpret this, what this means is that if you play the game many times in a row, you can expect to lose an average of 25 cents per play. And again, because of the way this is set up, you're not going to lose 25 cents on any one play, but that's just going to be your average loss per play over a lot of plays of the game. Now let's look at another example where we have a game. In this one, we're drawing one card from a 52 card deck. If a face card, a jack, queen, or king, is drawn, the dealer pays the player $5. For an ace, the dealer pays $8, and for any other card, the player pays the dealer $3. Find the expected value of this game for the dealer. So again, we need to create our probability distribution table first. The outcomes, or the x values, will be amounts of money, and since we are finding the expected value for the dealer, the amounts that the dealer pays out will be negative numbers because they're losses, and the amounts that the dealer receives will be positive numbers because they're gains. So our 3 possibilities are that we draw a face card, that we draw an ace, or that we draw something else. So if we draw a face card, then the dealer pays out $5, so the dealer loses $5. If we draw an ace, then the dealer loses $8. And if we draw anything else, then the dealer gets $3. So the 5 and the 8 are negative, and the 3 is positive. And for the probabilities, for the face cards, because there are 4 jacks, 4 queens, and 4 kings, that's a total of 12 cards out of 52. So our probability would be 12 over 52 for a face card. Since there are 4 aces, the probability of that would be 4 over 52. And for the other cards, remember that the probabilities have to add up to 1. So we could figure out how many other cards in the deck, which is 36, or we could just add up these 2 probabilities and subtract it from 1 to get our last probability. That way these 3 we know have to add up to 1. And let's look at our probability histogram too. Here are our 3 outcomes. We have -8, -5, and 3, and we've got our heights as our probabilities. So we can kind of see from looking at this graph that this is very much skewed to the left. Our highest probability value is the 3, so we could make a guess that the center of this data, or the mean of this data, would be sort of in the middle here. It would be more towards the 3 because the 3 had a higher probability value. So we could guess that it would be somewhere here, let's say between -1 and +1. Now, to actually find our expected value, we're going to take the table that we already had and add a column for x times p of x. And then in that column, we're going to multiply each x value times its probability. And again, if the x value is negative, we have to include that negative in our calculation here. So here we have 5 times 12 over 52. Here we have -8 times 4 over 52. And here we have 3 times 36 over 52. So if we multiply those and then add the results, we're going to have -60 over 52 plus -32 over 52 plus 108 over 52. That adds up to 16 over 52, or approximately 31 cents. That's our mean, or our expected value. To interpret this, this tells us that in the long run, after many plays of this game, the dealer can expect to gain an average of 31 cents per play. So how much money can the dealer expect to make or lose in 100 plays of the game? That would be 100 times the average per play. So if the game's played 100 times, the dealer can expect to make a total of 100 times 31 cents, or $31. Now again, this is an estimate. This is the expected value, but remember that these are all probabilities, so this is all based on chance.